welcome or welcome back. Delete as applicable, I guess. I've got a little project here, but I thought it would be quite good to make a bit of content on. What I thought I'd do is make a series of start to finish prototyping, so scanning, designing, printing, all the way up to actually making parts. I'll go over what this is in a second. You can probably already tell what it is. So today I'm just going to go over how to reverse engineer some of this geometry that we're going to pick up with a scanner using three tools. GOM Inspect, we'll be using that to create a plane across here, pick up some hole locations, all of these. Then we're going to go over how you can get that into Fusion, including the geometry data. From there, I'm just going to give a quick overview of how I prototype the part that we're going to make for this. What I might do is do a quick go over now of what this actually is. So this is a Volkswagen OA6, also known as a MQ500 gearbox. This is just the end casing. As you can see, it's quite a chunky thing. This is for my friend Jamie, who's as stupid as I am and likes to daily his race car. He keeps killing O2M gearboxes, so that's the older 6-speed. He's up around 600 Newton meters of torque now and stripping 4th gear, so this is an upgrade. This family of gearbox they're used in most commonly TTRS, RS3, older Tiguan, TDIs. But we've got a couple of issues. His Caddy is front wheel drive. This is originally a 4-wheel drive gearbox. These typically come up cheaper than the front wheel drive ones, so it makes more sense buying these if you can run them front wheel drive. Nobody, as far as I can see currently, makes a front wheel drive adapter of this. The transfer box usually bolts on here, the end of the diff comes up here and is splined, and then the drive shaft cup, it's not the same as an O2M. These ones run a spline stub, which causes issues. Obviously, then you've got to play around and run the different type in CVs and mix and match drive shafts, and we're going to see if we can get this in using standard drive shafts or bolt-on sort of replacements from other Volkswagens. So a couple of considerations we've got on this. To make the plate, we've got to bolt it on to these 4 bolt holes. Then in here usually sits a seal. I've removed it so I can get the sort of scan data in and around there. Now inside of that is where the end of the diff comes up and is splined. So we've got to account for that. What I think I'm going to do with this is run the original seal. The plate, obviously it's going to have to stand off to clear sort of these areas. So that's going to be stood off. We're going to have a protrusion out of the back of it that's going to seal on the original sealing area in there. Then on the top of that, I think it's about 4.5 mil that I measured from the top of here is where the new seal is going to start. So a couple of considerations with how we're going to do the backside sort of geometry on this. whether I'm going to just have the standoffs and then clear this entire area underneath. That's something we'll get round to. But what I'm going to do today is just do a quick scan and show you how accurate you can get with just a Revopoint Pop 3. Obviously the cheaper end of the sort of 3D scan market. I did do a test scan earlier just to sort of verify that this is going to be accurate enough, because we're not going to have much clearance around on the inside, but in hindsight we're going to have more than enough. So this is a quick scan I've done and a prototype. I manually measured these surfaces in here. Now this one's 83 and the one in there is 74. The scan, once I put it in GOM Inspect after cleaning it up in the RevoScan software, I created a fitting cylinder inside here and it came out 0.02 millimeters deviation, which is pretty damn good for what I'd say is a cheap consumer sort of scanner. It's not always that accurate, but for this, it's done really bloody well. Now this one, just to show you what we're working with, put that in there. Now I designed this with 0.1 millimeter gap on everything. So these are M10 bolts, and I think the holes came out, I think I'd done them about 10.15 maybe. But as you can see, that's gone on there. Get one of these in. You see that drops in. Now every single one of these drops in, locates, does up, and there is next to no movement on that. So we're going to be pretty damn good as far as accuracy goes with this one. Now before I waffle on too much longer, what we're going to do in the future is the bow housing, although it takes the earlier gearbox style slave cylinder, it's actually a deeper bow housing. So at some point I've got a scan down in there so I can machine a spacer just to raise that up. The dog bone mount that comes off here and goes down to the subframe, also different, so I've got to make one of those. Once this is all back together, I'm also going to be doing the process of scanning this gearbox, the old gearbox, one of the original engine mounts, and bringing it all into CAD together to make a new engine mount. Also going to be adapting the shift cables, so that's something else that will go on with it. So yeah, for now, so here we are set up for the scan. One thing I'll say is you want to make sure your part is positioned in a way that you can get around all the parts you want to without moving all that much. That helps a massive amount. I'll just go over to RevoScan. Just go over some of the settings quick. So this, obviously I want to do in high accuracy, feature tracking because we haven't got any marker dots, general object because it's not a face, color scanning off. I don't care about the sort of color data to make a texture, it's not going in a game or anything. Face removal off, auto exposure. I'll start off in auto. This might cause a few issues here and there because it's a cast aluminium part and we've got a machine surface. Some smooth sections, some sort of rough. I've got a light directly above, so shadow shouldn't really be an issue. But as we go through, you'll probably notice some areas are underexposed, some are overexposed, so I'll go through. There's a control on the back of the scanner so we can adjust the exposure on the fly. Now, scanning distance, I'm going to keep this around 500. Some scans you might want to start off with a bigger sort of scanning distance if it's got a lot of sort of circular or repeating geometry. This shouldn't be too bad because there's a lot of unique points around it, but you'll find the sort of stuff with a lot of circles, repeating geometry, things like that, it will lose tracking. So having the bigger scan distance, it allows you to start off further away, capture as many sort of unique points as you can at the very start of a scan, just so it's got a decent base as you go on. That's pretty much it for the settings, so I'll just jump straight ahead to scanning. Now, you don't want to rush this, but at the same time you don't want to take too long. You might think the sort of longer and bigger the scan, the more accurate it would be. What you'll find is you'll pick up a lot of sort of garbage data as you go through. So the sort of bigger, longer scans tend to have a lot of points where if you wobble the scanner, for example, it will end up with sort of ghosting on the scan. Now, the bolt holes, I like to try getting them from a few different angles just so we can pick up as much data inside them. Most scans that's not really an issue, but we'll be using at least a little bit of the bolt hole sort of depth to create a cylinder in GOM Inspect, which you'll see. Now, we do want the sort of geometry and the data of this sealing bore. We don't need to get all of it. GOM Inspect does do a pretty good job of sort of interpolating out. I think that should be pretty much all we need. We only really want that top face. Now let's just assess. I think that should be pretty much all we need. Obviously we've got a lot of stuff we don't want. I'll show you how we can get rid of that. So to start off with, we'll just complete that scan. You see, it might not look much, but as you zoom in, you can see all the individual points that it's picked up. And we've got some quite dense sort of scan data everywhere we need it. I think I'm going to be pretty happy with that. Now, the first step is you want to fuse the point cloud. You've got a couple of options, advanced and standard. There's a little write-up about it there. You can pause and have a quick read if you want to, but for this, I think standard. And we're going to go as detailed as we can. Now, this might take a minute, so I'll fast forward. So we've got our fused point cloud. See there is 43 million. Now this is going to make my computer run pretty slow. So what we'll first do So we've got the fused point cloud now. There is 46 million points, which is going to make this computer run pretty bloody slow. So what we're going to first do is remove as much of this scan as possible, all of the bits we don't need. We'll just move that as best we can with it being slow. Now we only really want that top face. Oh, this is going really slow. Now that'll just select that area there. We can remove all the bottom portion just by hitting delete. That's dropped it down to 34. Might be a little bit more manageable on the computer now. We'll drop that down some more in a minute. So, next step is isolation. Now this basically goes through and removes isolated points like these ones out over here, and a lot of the points, the garbage points that are sort of floating about. Now it does it at a ratio of the total point cloud. Some scans, if you've got areas that you've scanned that aren't connected, now this will go through and remove them. This shouldn't be an issue, so I'll probably leave it somewhere around there. Now this might take a minute. Well, that took a while. Probably didn't need to go quite as detailed on the fusion, would have cut down on a lot of time. Fast forwarded it back, but that was probably about 10 minutes. Now it's selected all the isolated points that it's detected, so we'll hit apply. That will just go through and remove those. Now the step after this is upon overlap. That basically picks up overlapping points, so we can do that. You can see that's tidied that up quite a lot. So up to the overlap now. We're not going to be doing any smoothing because we're going to be using sort of the GOM metrology software. We want basically a clean, unedited sort of reference point. Just go through and do the overlap detection now. Now the overlap detection is finished. It's picked up quite a bit, so we'll apply that. It might take a minute. Now that's going to go through and just remove all those points. Now before that we were at just short of 34 million points. We'll see what that takes us down to. Now I probably will run a simplify on this. 23. I think I'll leave that there. We should be alright. Now you can see that it's tidied it up quite a lot. I won't move it about too much because it will slow the computer down. It looks like we've got pretty good defined detail. It doesn't look all that great now, but we'll just run the mesh. We'll do that on the maximum quality. Now, as you can see, we've got a pretty high quality scan now. We've got good detail up on these top faces, which is good because we'll be using these points to set a plane. We've got a little bit of detail down in the bolt holes. Some of it's been removed through the isolation process, but it shouldn't matter too much. GOM Inspect should be able to interpolate even just based on that little bit that's left there. We've got a good smooth scan for the most part on that inside bore. We could have spent a bit more time on that, but for this I'm not interested in the overall accuracy of the measurement there. All I'm using that for is a center point. So as long as that's within, you know, like 0.1 millimeters with not all that much deviation across the scan, it'll be fine for our need. I'd call that pretty good. Now we're just going to go through, we'll export this as an object file or STL, and I'll get it over into GOM Inspect. Now over on the Windows computer, unfortunately GOM Inspect doesn't run on Mac. Now it's part of the Zeiss Quality Suite. It's an incredibly powerful bit of software and I have no idea what 99% of it does. I won't give information on how to install it. I'll drop the link on where you can get it, and obviously you can go through, but I don't want to make the video longer than it has to be. It's pretty easy to go through. You've got to sign up, but once you've got it, you need the Inspect Optical 3D. We'll just start that. Now we want to do a new project. Now we want to import the part. I imported this a second ago just to test it, but it's easy enough. Insert it as a new part. Units, millimeters, you don't want to import in inches or feet because it will be absolutely huge. Okay. Now once it's in, you can see there's plenty of detail in there. I've got a feeling this one's going to measure out pretty good. Now the first thing we want to do is just align this to the global coordinate system. So up here, create alignment 3, 2, 1. Now there's plenty of options for this one because our main plane is going to be this. I want that on Z. So I've selected ZZZ, YY, X. Now we want to control click the points. So we'll go one here, one here, and one here. That will create the plane there. Now the next one, just those two there. Now for that X one, I'm just going to put it somewhere around here. Now as you can see, we've got X along that way, we've got the Z, there's the Y. So when we bring that into Fusion, it'll be a hell of a lot easier to work with. And we'll just OK that. So there is so much to this software. We're only going to be using really the plane and cylinder options. So to start off with, cylinder, fitting cylinder, we want to select the best fit option there. Now we'll just control and click a point inside here. that will just go through and do a best fit cylinder. You can see the points where it's touching, where it's not. It gives you a little report here. So to start off with, if we just create and close that, actually we'll do another one quick, just because I know we've got 2 data points there we can just verify with. So we'll do another one inside there. Now, like I said earlier, I measured these up manually on the actual part, and I know that one there is 83, I think it was, and that one's 74. So we can go up here into inspection, check dimensions, other. Now as you can see, there is a million options here. We just want diameter. I want to find over here in this little tab, elements, fitting elements, cylinders. No, I think I've got to select it first. There. Right, inspection, check dimensions, other, diameter. Now, you can see there that's 0.02 millimeters. So, not even a foul out on that. For consumer grade, couple £100 scanner, that is absolutely perfect. We'll just check the other one. I'd hope it would be about the same. Even better, 74.01. So we know that that scan now is good to use, very accurate. Now we'll do a few more cylinders because we want to know the location of these holes. Now you can see there's barely any data for it to pick up there, but this software is so good at sort of guessing and doing a best fit. We just control and click inside there. There we go. Create, you can see that's created a near perfect cylinder to where it thinks the rest of that data should be. We've created that, we'll just go through and do the others now. Create that. Looks good to me, create that. And create that. Now you can already see that they're pretty accurate, even on the very little data it's got there. And we've got all the cylinders we need there. One thing I will note, this is really useful. Not only does it do inner cylinders, you can place a cylinder in there if you wanted to know what that radius is. So you can see that's really good there. Also things like this. Let's try that one. See, that's doing a cylinder based on that dimension there. So another example, let's say in there, you can do an outer. So as you can see, very good bit of software. There's a hell of a lot to it that I have no idea how to use. but for our use for this simple part, it's absolutely perfect. Now the last thing we want to do is just make a plane. I think what I'm going to do here is a 3-point plane. So 1 point there, 1 point there. I don't want to get too close to the outside or the inside where the scan data might be a bit iffy, or you know, there's a taper from machining or anything like that. So doing that, we can see the areas it's touching, the areas it's not. For our use, that should be absolutely perfect. Now everything's good there. We've got the bits of data we need. I don't want that second cylinder really, that's not really of any use to us, so I'll just remove that. Now that we've got all our data there, we can export the parts. So in the geometry section, we've got IGES. So let's do that. Export in one file, millimeter units. Now we want to select all of our cylinders there. And the plane. So now we've got all that selected, we can just export that. Let's change the name because I selected it all. Let's just call that transfer box geometry. Okay. Now the next one, we want to export the mesh as an STL. We've selected the mesh there. Let's do TXB mesh and export that. What that does is we've got our modified mesh with the correct global coordinate system and our geometry both exported to the same coordinate system. So when we bring it over into Fusion, everything lines up. Now I'll transfer that over onto the Mac, get on Fusion, and we'll take it up from there. Now we're back on the Mac, we've got Fusion open. For this part, I found that uploading the files through the data panel doesn't always work properly for some reason. So for this one, file, open, we just want to go open from computer. I start off with the geometry file. As you can see, that's brought it in. We've got top plane, front. You can see both cylinders. Now you can see some of them are a little bit wonky. That's just because the scan data wasn't great. That doesn't really matter all that much. Now we'll just go into Insert, Mesh, select from computer, and we'll bring that mesh in. We'll OK that. You'll notice that the mesh isn't a great quality in here. That's just Fusion settings favouring performance. If you've brought it in and you notice it looks a bit dark and you can't really do anything with it, like that, that's just the display settings. You just want to set it there to shaded. That's a lot better. Now, this is our plane we made for those mating surfaces. So we just want to find it in here. It's that one there. Now we want to construct a plane, and we'll do an offset plane. Offset 0 millimeters. Now that is the main plane that we're going to be working from. So we'll create a sketch on that plane. Now we want to go up to Create, Project, and we just want to project up all the cylinders we made. Like that. So now that we've got these points, we can mostly assume that they're the center points. We know that these are going to be using M10 bolts, so we can create some circles here. And I'll just make them 10.2 millimeters, just to give us a little bit of wiggle room and account for any errors. That's still a lot tighter than it needs to be in this case. And that's like that. Now, this circle here doesn't really mean much to us with that diameter. The seal that sits in here is an 83mm diameter. As you can see, the measurement there is 83.221. We don't actually care about that. All we want to know is what size the protrusion needs to be. Now, I've done some digging and found that that seal is 83mm diameter with a 65mm inner. So if we make this 65.5, that's the part that's going to poke out of the back of the plate and actually sit inside the seal. And we've got that. Now we've measured, and the shaft that comes up from the diff is 53mm. So that's that there. Now we need to avoid that when we create the wall for this. So this protrusion, let's say, let's make it 58, and that gives us a little bit of space around it to allow for any misalignment. And we've still got a 3.75 wall thickness there, so it's not going to be a fragile sort of part poking out the back of it. And we'll say OK there. Now I want to hide the projected geometry, so we're only working with these bits. What we want to do now is create the basic shape of the plate. Now, a couple of things to watch out for. This part here obviously is where the bell housing bolts onto the block. So we want to avoid this area. Now we've created all the geometry we're going to be using. Now we know they are a 10.2 bolt hole. But for the actual feet that are going to extend down, let's call those 24. Gives us a little bit of wall thickness there and a stable platform. That's all those. Now to rough out the basic shape, what I like to do is use the line tool, start and finish it beyond where we actually want, and we're just going to use the tangent constraints to bring it down. If you find that you can't use the tangent constraint and it won't move, it's probably because you've drawn the line with a constraint. So if it's snapped to anything, or if you've drawn it perfectly vertical or horizontal, it will have a horizontal or vertical constraint on it, and you won't actually be able to do that. So you notice I draw them at a line away from everything and just allow the constraint to bring it in. I'll do the same thing again here, just bring that across. Trim as we go, just to make sure we don't end up with them little bits hanging about later. That's perfect. Now, like I said, we want to avoid this bit here. So what I think is my best approach is go roughly into the center here. We'll make this circle here, like that. Now I'll create another one here and just bring it out to the edge of there. What that will allow us to do is if I just fix these in place by clicking them, right click, fix. That's so it can't move about. That one's fine because it was created from the center point there. That one, because it wasn't attached to anything and constrained, if we then went to, in a second, make a line up to it, it could move. So now that we've got a couple of circles there, we're going to use this area here. Actually, we just want to bring that in a little bit. Move constraint there, because we don't want this part here to go over into the Bellhausen sort of area, so we'll bring that down so it's away from there, and we'll just bring that one out. We'll have to unfix it. And we'll just bring it out and use the tangent constraint to lock it there. Now I'll just fix these back again. What this allows us to do with the line tool, I just draw a line up here, make sure it isn't constrained to anything, and we'll actually tangent that to that, and now that to that. I like the look of that. Now we'll trim this off. We'll have to go in and trim these little bits. We'll actually trim that and that. And what you can see now is we've got a nice gradual line, a nice radius up. It hits here, and then it will sweep out and around here. Now we can remove this, and you can see nice swooping line, hits up onto here, comes around, and what we'll do now is just create a tangent between there and there, there and there. Now that's closed our shape in. You can see we've got a nice shape to work with. And what I'll do is finish the sketch. Right, my screen capture software went a bit funny there, but we're back. Now, let me just turn on my timeline. For some reason that was gone. Now, we have got our plane there. The back side of the plate, I think I'm going to have it starting around here and the feet going down, just so I don't need to do too much sort of roughing out and pocketing on the back side for no reason to clear all this. So what we're going to do is just create a new offset plane based on that, and get on the true dead on side and just bring it up just slightly above that protrusion. Now that we've got that, we're going to extrude, get rid of that plane there so we can actually select stuff. re-enable it. Now we're going to start from object and just select the bottom plane, extent type to object and select that top one, new body, OK. As you can see, we've now got those 4 little standoffs that come up above everything. Perfect. We'll re-enable the sketch because Fusion likes to disable it once you've done a extrusion. We're going to select the feet and the top part. Select those. And these. Now we'll just select all of that. Re-enable these planes, and we want to start from that top plane, extent type. But now let's just go up 14mm. We'll set it to join so it actually attaches to those. You'll notice these bodies up here just go down into one. And we'll disable that and the sketch and the planes, get rid of all that geometry. As you can see, that's already looking exactly how we want it. We've got the standoffs. I'll re-enable that mesh and you can see nothing's touching. That's absolutely perfect. Now, that 53mm probably shouldn't have extruded that up. So extrude, bring the sketch back in. We can actually select that part there, which is the bit we didn't want to extrude. Bring it up and do a cut operation. So now we have got 58mm, which is the outer section of the protrusion. Now we want to go down roughly the seal depth of that. Yeah, okay. Bring that in and we can work off that. So what I'm going to do here is inspect, no, construct, where are we? Inspect, section analysis, just select that plane there. You can see we can drag through and just see where we are. That allows us to come in here and we can see that area where the seal usually sits. What we'll do so this is the protrusion. We'll start it from the bottom of that plate. And we'll just bring that down. Bring it down to about the, where are we? Extent object. We'll just bring that down to that plane. It's not letting me. 13mm, that's fine. Get rid of the analysis, get rid of the mesh and sketches and construction. You can see we've got a plate with a protrusion that's going to go down and seal. The only thing we've got left is the seal that actually goes inside here, the new one, to seal the driveshaft cup. That is a 65.2mm diameter seal. That sits 4.5mm above the top lip up here, so this plane here. So the start of that, we'll do an offset plane, 4.5mm up. Get rid of that other plane, and do a sketch on here. And we want to create, project. We'll just project any of these circles. They're all concentric to each other. That way we can use that center point to draw a 65.2mm circle up there. Now that seal is 10mm deep. We'll hide that sketch. We've got our 65.2mm diameter circle there. It starts 4.5mm above that lip. And we want to select that. We know that seal is 10mm deep. So we'll cut all the way through there. I can measure from that face to there, and you see that's 9.5. So we just want to extrude that face up another 0.5mm, and that's everything we need there. We've got the plate, the protrusion that goes into the seal in the gearbox, the feet standoffs, the bolt holes, the seal. This is this area down here. And that's all absolutely spot on. Now I think what I want to do is just sink the bolts rather than having them sticking out of the top. So we'll do a counter bore. From memory, an M10 cap has a 16mm head. So we'll just make that 16.5. Now we can select the centers of these because I'm doing a sketch directly on the top surface. If I wasn't doing that, I'd have to project the geometry up. And that's fine. I believe the heads on most of these is 10mm. Let me just measure one. 9.96. So take that down 10. Now we've got the plate absolutely perfect there. Now that that's all designed, we're just going to go into 3D print, select that. That should bring it into Walker for us. And we want to print that face down, something like that. Now I don't want any particular strength in this, just want it as quick as possible. Enable support for that little under section. Don't want any brim. That looks good to me for a print. So I'll hit print on this, do a little time lapse of it being printed, then we can do a test bit. Got the print. I'm an idiot and used the wrong filament profile, so it doesn't look great, but it's a print nonetheless. It's got a couple of bolts here. Now, we made the bolt clearance holes 10.2, so there's only, 0.1 mil around them, so any fitment issues should show up pretty quickly. I'll get one in there. There's one. There's two. Now a moment of truth. Straight in, no problems. Last one. Absolutely fine. As far as I'm concerned, that's an absolute success. Not touching anywhere under there. Everything's exactly as it was on the CAD. Now, we've got the cup that we're going to be using. This is the sealing surface here. That's going to drop down inside. That seal's going to ride on the seal inside there. Happy days. Right, for the next video, what I think I'm going to do is do a complete rundown of how I set things up in Fusion, setting the stock size, selecting the stock, the cam, toolpath, operations, all the considerations I've got with this, because obviously it's going to need machining on both sides. So I'll go over on a part like this where I haven't got a sort of right angle. What I'm going to have to do is probe on this circle and then either align this to my X gantry so it's parallel, either that, or I'm going to use that as the center and then use IO sender, which is the control software for the machine. I can actually probe off 2 points on here and it knows what angle that is on the workpiece. So either way, we've got a few things to go through. I think the video after that will probably be some of the other bits and pieces on here. Like I said earlier, got to do a spacer in there, dog bone mount, the actual top mount to mount it into the car. That's going to be quite a fun one because we've got to scan both gearboxes, scan the original gearbox mount, bring them all in together, and then see what's going to work. So for now, I'll call it a day there. This video is probably over an hour long at this point. Thanks if you've watched it. There should be a lot more coming. I'll be putting a bit more effort into videos as and when I get time. So yeah, thanks.